Yeah, I have shared the presentation to Sirish M. Bajpai.
Okay, sir.
So he can share the PPT actually.
Yeah, okay, sir. Yes, sir.
Hello. Yes, yes, I have sent in WhatsApp actually. WhatsApp, WhatsApp. Yes, yes. Start his presentation. So whenever move to the next slide, we say next. So on the next. यहाँ से शेयर करो.
Hmm. So you can start the presentation. Is that visible at your side? Sir, are you there? Balaji, sir, are you there? Sir, if you are there, kindly unmute yourself. Yeah. Hmm.
Hello, my voice is audible, right?
Yes, sir.
Okay, okay. So the topic that what I have chosen is like a biometric generation using the GAN, and we have to discriminate using the Siamese network. Okay, so there the biometric consists of various biometrics such as like the fingerprint, and then the the face, and then the signatures. So in our HCL ERS, ERS means an engineering research and development. So one of the team members that they have, one of the our clients, I should not take the name of the client, but they came us to design a fingerprint for a particular user actually. So now the challenge is that the face can be retrieved on the the Facebook or an LinkedIn, uh, from any other social medias, but the fingerprint is unique actually. So then, because it has the ridges and valleys for any particular person, that is the unique edge. So the next slide. So then we generate the fingerprint detection, like the face the biometric fingerprint generation using the GAN networks. So then when once we started with GAN, so the generation was not up to the mark actually. So then once again we have used SR GAN. SR GAN means a super resoluted GAN actually. So to clearly discriminate the ridges and valleys associated with each fingerprint. So then when once we generated the multiple copies of a data for a particular user, then we pass to a discriminator. Yes, the discriminator has to discriminate whether it is like a real genuine fingerprint or it is a generated one actually. Or generated one is like fool's you know the masquerader one. So providing the false data, the generated is like a false data one. So for that, we have designed a discriminator using the CMS network. Actually. Okay, so can you go to the next slide? Yeah. So here the fingerprint generation. So here when once we see the fingerprint actually, okay. So here it has when because for this it cannot be recorded by using the normal camera actually. For that, a particular sensor, the cameras associated with the particular sensors will be there to capture this fingerprint actually. So when once we see here in the left figure, okay, so here it has the ridges as well as the valleys and some of the dark lines and some of the crease lines and some of the the adjoint lines. The lines are not continuous. This remains unique for a particular subject or particular person actually. So now the generation of these multiple copies. So when once we generate it, it should resemble same as that of the original fingerprint actually. So that we have generated by using the GAN network. So generator as the GAN network is one of the generator actually. So for that, when once we analyze the things, then we have moved on to the super resolution GANs because the resolution was not proper for a particular fingerprint actually. No, not for a particular fingerprint, for all the subjects actually. So that's why we have used the super resolution GAN. So can you go to the next slide? Yeah. So here, the fingerprint generation, it is one of the the crucial task actually. And here, this fingerprint generation, nobody has touched upon this uh, because of two things. One is recording has to be recorded by the particular sensors. Okay, because it is not recorded by an actual mobile phone camera or any kind of thing, but it has to be recorded with a particular sensor. And a small the ridges or valleys, if it is absent in the generated data, then there is no point in discriminating that the full data actually. So the skilled fingerprint generation in such a way that it has to resemble that the original face actually. Okay, so this is how the security people, this is actually this project came from the defense actually, uh, defense part of the near the Pondicherry actually. So it is in the down south. So from this defense people, they approached us like you need to design a multiple copies of a particular user so that it should resemble same as that of an original fingerprint. So here, this by leveraging this advanced AI technique, we can have the higher fidelity and diversity in the generated of the fingerprints. So this is how we generated the fingerprint by using the GAN networks, and then the resolution has been modified by using the SR GANs. So that I will be explaining further. So can you move to the next slide? Yeah. Here the GAN is like generative adversarial network consists of two neural network actually. Okay, so one is on the generator part. The generator tries to generate the data and to fool the discriminator, and discriminator tries to discriminator evaluates the authenticity such that yes, the whatever the generator that has provided, that is a the false data for this particular subject. If the generator provides the negative part of the data, so it has been like the false data actually. So if a generator is provided the original data, so then the discriminator can able to discriminate, yes, it is a real genuine data actually. So this is how the each network will fool the other network actually. So the generator and discriminator, when once we see the trending laws, when once we design this neural network for any application, this for one such application that we have chosen is fingerprint biometric, and this was a recent work. It was deployed in Pondicherry BSF actually, Border Security Forces of their army officers, means in their office we have deployed this. This adversarial process lead us to improve the quality and then the generated output. So this is how the GAN network will work. So can you move to the next slide? So I have skipped the mathematic part of the GAN network because when once we optimize it, we uses uh, the optimizer to optimize the weights associated with the neural network of the GANs. Actually. Okay, so for that we use the conditional optimization. Subjected to this condition, we need to optimize the data. So this is how the architecture diagram that we have are designed actually. So this is a random noise. Okay, the random noise means in it may be a fingerprint, or it may be a temporal data of a signature, or it may be a face, and it may be a voice recorded data. So that will pass to a generator. It will generate the data, and once again, when we have the real as well as the generated data, we will discriminate this, which one is a real and which one is a generated data, and then it will give the discriminated out. So this is how the flow of the workflow that we have done by using the GANs. Okay, so can you move to the next slide? Yeah, here the comes the super resolution GAN. As I have mentioned in the uh, 1 minute, I have to someone is joining, I have to admit it. So when once we analyze the things that we for the using of the fingerprint generation by using the GAN networks, okay, the resolution was not proper. Okay, so when once we see this example of the tiger face, when so this is not an actual tiger because it's a generated one, because in Gen AI, so the generated one is like any user can able to discriminate, no, this is not a generate real tiger captured image, this is a generated one. So we need to resolute this image. Okay, so the eyes part is not properly visible, and then the nose part is not properly visible, and then the wrinkles associated with the tiger, these black spots, okay, this was not completely visible by using the GANs. So then we have used the super resolution GAN by changing the math actually. Okay, so the mathematics associated with the GAN network. So we have changed the network actually. Okay, then we have incorporated the resolution by using subjected to the constraint optimization, because it's a constraint one actually. Okay, so the math part I have not embedded here because it is like we don't strictly concern about the math part, but we will strictly concern about the loss trending curves. So that we have I have embedded here in this slide. So when once we subjected to this constraint optimization, so these black spots will be clearly visible in the super resolution GAN. So can you go to the next slide so that it will be completely visible, completely understood by the people actually. Yeah, here when once we analyze the things by using the SR GAN. See, when once the benefits of the SR GAN, is in such a way that we have a very good clarity associated with the fingerprint ridges and valleys. See, when the first row, the top right one, okay, first row, the third column, okay, top right one, the ridges and then the line, the crease lines associated with the fingerprints are like, generated with a very good resolution. There's the detailed information is there, and then the clarity is there, and there is a high quality of the data is there actually, because fingerprint is such a one such a biometric that requires a high quality of the data actually, because we do not have any, because it stands unique for a unique subject actually. So when once we analyze the second row, the first column, so the crease lines, the curved lines are more generated as if like it resembles as a original fingerprint. Okay, so this is how enhancement has been done by using the super resolution GAN. Okay, can you move to the next slide? Yeah. So this is the original generated one, and then this is a you know the data that we have given is positive, and then the negative class. The positive class is the real genuine the fingerprints that we have recorded from all the employees of that unit of BSF unit in Pondicherry. Then we have created a multiple copies for each and every subject. Then we have passed to uh, the discriminator network. This is one of the discriminator network, which is a Siamese network. Okay, it tries to discriminate by using the activation function such as ReLU. And then yes, when once you pass this, the discriminator says no, it is a, the generated one. When once you pass the above one, so yes, the discriminator will say that yes, you have passed the real genuine fingerprint actually. So this is how, even though they look the similar in patterns, similar patterns are there in both the real genuine fingerprint as well as the generated one by using the super resolution GAN. But our discriminator is designed in such a way that by using the Siamese network, it will able to discriminate between the generated as well as the actual fingerprint actually. So this is also one of the subjected to constraint optimization that we have designed by using the optimization techniques. When once we design the CMS network, we looked upon all the activation functions like, tan hyperbolic, ReLU, and then the simple sigmoid function. But the activation function of the ReLU is such a way that, because in the generator is designed as the generated fingerprint, there's a one such crease lines has been missed among the millions of crease lines. Okay, so I will repeat this sentence. There are millions of crease lines, but the generator might fail to generate that the copy of the fingerprint of a particular subject. Out of 1 million finger crease lines, only one or two might have missed. So that two divided by 1 million is like, negligible amount. So by capturing that information, the discriminator able to discriminate uh, uh, the genuine one as well as the generated one actually. So this is how we have designed the CMS network. For that, at the activation function, ReLU was giving much better result as compared to other activation functions actually. So can you move to the next slide? Yeah. So now we have three networks. One is the generator advisory network, as well as the SR GAN, as well as the discriminator. Now we will plug and place these two networks. One is SR GAN, we generate using the, you need to, generate the data with a good quality of resolution of a fingerprint. Then we will pass to the discriminator, which is a Siamese network. So it tries to discriminate the data actually. So we, by combining these two networks, we can able to design the uh, uh, NF, counter spoofing biometric thing actually. The counter spoofing biometric can be anything, whether it is face or a signature or a fingerprint. But the GANs or the super resolution GANs, that what type of network that we need to use, that depends upon the type of biometric that you are giving it. So it may be a temporal biometric, it may be a image type of biometric like face. It may be temporal by using the signatures. It may be a resoluted image like fingerprint. So all these things you can able to generate by using the generator network. So the network that you need to choose is based on the type of fingerprint that you need to uh, design it, actually, that you need to generate. Okay, so this is what we have inferred from these network. And finally, a discriminator can be anything, actually, a simple discriminator network, or you need to go to the complex network such as CMEs and all these things, or you need to embed by using the transformer based network also. That is also possible. That is on the next pipeline, that when in the next upcoming seminar, because that work is being carried out that we have not published so far, by using the reinforcement learning, using the context based transformers, that currently our in our industry these type of works are going on. So this is how we use these GAN networks and super resolution GAN to generate the fingerprint biometric. So can you move to the next slide? Yeah. So so this is how the original biometric, and this is how the generated biometric that we have transformed this data, the original data, into a generated data. Okay, by using the super resolution network. This is how that I have explained by using the SR GANs, actually. So the crease lines, there are millions of crease lines. Here also there are millions of crease lines, but there is a one such crease line. Even the SR GAN may fail to generate that, actually. So that the discriminator can able to discriminate. Discriminator is like, even if I provide a 99% accurate of the data, the discriminator has to discriminate. No, this is a even 1% of the data is missing in from the entire data, actually. So in that way, the discriminator will able to discriminate the things. Okay. So can you move to the next slide? Yeah, this is how the CMS network, the GAN role, actually. So so here the fingerprints, even when we have conducted experiments by adding the Gaussian noise also for a fingerprint, actually. Okay, because there are certain scenarios, the fingerprints may not be recorded in the in a closed environment or in a constrained environment. The fingerprints may be recorded in the in an unconstrained environment. So the random noise will also add it to the network, actually. Okay, so because of that, actually, so we need to so because of that so the random because of that the random noise is also embedded in this fingerprint, such that the discriminator even still able to discriminate which one is the real genuine fingerprint, and which one is the closed which one is the generated one. So can you move to the next slide? Yeah. So here we will design two labels. One is the positive class label, and another one is the negative class label. The negative class label is like, the generated one, the fake images, and then the positive class label is like, the real generated images. Okay, so we'll pass to the discriminator. So it will predict the label. Okay, so the label means, if it is, the label is negative, means yes, the given test images is negative. Even we have evaluated the metric also. So can you move to the next slide? Uh, so to further, refine the art, to improve the quality of the work, actually. So the discriminator based CMS network we have implemented, actually. So this was the very good approach that we have developed, and the customer is also happy. So. Even they have got a feedback in an unconstrained environment also, even though we record it, so it will able to discriminate it, actually. Okay, so can you move to the next slide? Yeah, so these are the some of the data set that we have used. So we have collected first initially the major army unit people, which is about 80 different people. They have we have recorded the data, and then we generate this multiple copies of 80 subjects. Then we've tested across all the range of fingerprints actually, 1 versus 80, 2 versus 80, so 3 versus 80. So all the one subject, it has been compared about all the 80 fingerprints. Then we have scaled up to the 200 people, because the people of the people they working there in the army unit is to roughly around 200 to 250. So we have scaled up to the 250 to 300 actually. So that was the very, even though when we scaled it, it was giving a better result uh, with some optimization technique. Actually, some of the hyperparameters have been tweaked actually. So can you move to the next slide? These are all the experimental based approaches. Can you move to the next slide? Yeah. So these are the some of the experimental analysis. See, first we will see the loss trend curve. So the loss curve in the top left is the loss curve. Okay, we have reached up to the less than 1% of the loss. Okay, uh, this is a generated loss, because the generated tries to reduce the loss and discriminated tries to increase the loss. So here the generator and discriminator, they go hand in hand. They will settle down in a common point of near at about the 50% actually. Okay, so in the top right curve, the GAN loss curve, the above one is the generated loss, the below one is the discriminator. They will try to segregate constant. They will try to become a constant after certain epochs actually. So that particular epoch, up to 80 epochs, that we have to run it. So when once we analyze the distance between the cosine distance or KLD loss between the generated as well as the original fingerprint, the KLD loss was found to be the 2% actually. It is 2%. The in the table that we have shown, the KLD loss is 2%. And Mahalanobis distance, because we have compared the Mahalanobis distance, because the data was varied about 80 subject to the 200 and 250 users. Because of that, the variance associated with that is been captured actually. The variance is also less compared to because the fingerprints that we have, it has been generated by the GANs, it was very good actually. It was, the crease lines has been clearly captured, so that's why the Mahalanobis distance was also less. Okay. So can you move to the next slide? So these are the experimental analysis that we have performed. So actually, even though there are the model is working fine, there are certain challenges associated with that actually. Okay, so currently a reinforcement learning is beating the era actually. So and then with respect to other architecture, and with respect to the same architecture, some of the, even though we might have run to the 80 epochs, the model might have overfit that actually. So we need to generate. So there is no hard trade-off between the loss curve should be exactly 50%, and that the discriminated loss accuracy should be also 50%. There is no such number that it has been came for us when we conducted several experiments, but we have tried to minimize that experiment. We have came across approximately 46% of loss we have achieved, and then the 52% of accuracy that we have achieved by using the discriminator. 42 of loss of generator and 52 of discriminator. So in this way, we try to balance with each other actually. So this is how some of the challenges that we have faced. So these are the things from my side. So the next slide that we have. Yeah, the future directions, this can be deployed by using the RL, by using the for any of the biometric, that a 3D biometric that can be deployed actually by using the 3D one. So, so these are some of the feature directions. Can you go to the next slide? Yeah, some of the case studies that we have generated, we have conducted certain experiments. Some of the case studies in the real world application, where even we have taken our own fingerprints and then we have tested on our own office actually. So some of the case studies also we have done it to showcase to them as a proof of concept actually before when we actually deployed for them. So that case studies also that we have done it actually. So this is also a part of that network actually. So can you go to the next slide? Yeah. So in conclusion, SR GANs is one of the very good network in designing the resoluted biometrics actually. So then SCM's network is a good discriminator network. This can be applied to any of the biometrics actually in the security based application actually. Okay. So these things are from my side actually. So thank you uh, for the things that I have showcased from my industry.
Thank you so much, sir, for that insightful presentation. Audience, any questions from your side? Any questions? So since we are having no questions, we'll move with our next invited talk by Dr. Suman Lata Tripathi. Topic.
Yeah, I would like to thank Dr. Sumanlata Tripathi also because she was also one of my colleague and even we have worked for some of the research work and uh, I give my sincere thanks to Integral University as well as the Dr. Uh, Shrish Bajpai for sharing the slides and all these things for conducting this seminar in a smooth manner. So thank you all for this opportunity.
Yeah, thank you, sir.
So can I leave? I can leave.
Yes, sir. You may.
Okay.
So we'll start with our next invited talk by Dr. Suman Lata Tripathi. The topic is FinTech for Analog Circuit Design, and she will be joining online. Ma'am is a professor in the School of Electronics and Electrical Engineering at Lovely Professional University, Punjab. With over 22 years of experience in academics and research, she has made significant contribution to the fields of microelectronics and VLSI design. She has published over 125 research papers, 14 Indian patents, and 4 copyrights. She has guided multiple PhD scholars and organized numerous workshops and conferences. She has received several prestigious awards, including the Research Excellence Award and the Women's Achievers Award. Please join me in welcoming Dr. Suman Lata Tripathi, ma'am.
Thank you very much. And I'm very thankful to the convener of conference, Dr. Series, and the university chancellor, vice chancellor, and I'm very thankful to I'm very thankful to Dean Academics and head of the departments, faculty members, those who have invited me to join this conference as a speaker. So this is my one of the 4 area of research, which is FinFET design and their applications. So I'm just going to start with this. I hope my screen is visible. PPT
Yes,
is
ma'am, your screen is visible.
Okay, thank you so much. So this is my topic of today's discussion is FinFET for analog circuit design. So mostly the researchers have worked on the digital design part with the FinFETs because of some reasons. And the reasons majorly there are the you can say low power consumption and the speed of operation even at lower technology nodes. Why? Because when we talk about the CMOS technology for any kind of integrated circuit, so up to 45 nm technology that provides good responses in terms of power consumption. But when we talk about below 45 nm technology node, then nor conventional CMOS does not provide that much of efficient in terms of power. So then FinFET take now some of the products are available with the FinFET technology only, like mobile communication and all, by different companies. So TSMC and Samsung. So but most of the applications are there for logic and processors, digital circuits. So there are still scope to explore FinFET technology for analog circuit. Many researchers are already working in this area. So that's why I have taken this topic for this conference purpose. And recently, I have also got one uh, funded project from DST related to FinFET for analog RF applications. So let me start with this. So my discussion include introduction, need and challenges, MOSFET versus FinFET, and FinFET architectures, the possible FinFET architectures, performance parameters, conclusion and future directions and references. It is not moving. Yeah, now it's moving. Okay, so need and challenges. So I already told you that below 45 nm technology node, the problem of with CMOS technology is the power consumption majorly, and because of that reason, you cannot pack more transistors for further increase in the application part. So that's why this kind of FinFET technology or similar kind of multi-gate technologies stay. Trying to replace the CMOS based technologies in integrated circuit. And the increase in drive current improves the circuit speed. So how increased in drive current here on the same technology node, here the number of gates will be more. In fact, are available in double gate and triple gate format. And means like if you compare here with single gate MOSFET, this one is single gate MOSFET, where the number of gate is only one, and the size for the similar kind of size, if we make channel vertical, here the channel is planar only, but if we make channel vertical like here, so we can place gate all three sides of the channel. So overall conducting channel will be 3 times. Means you can say 2 times height of fin and width of fin. Okay, this width of fin. So overall, this is effective width of fin. Effective width of fin. So this way, even with the same dimension, we can increase the number of gates, and by that we can increase the conducting length. This here there is length L only, but here the length is two sides, top length and two side length and top length. So total length will be this much of, which is increased in comparison to the single gate MOSFET. So if width will be increased, so drain current is directly proportional to W by L. So if the effective width is increased, it means your drain current will also be increased. So for the same dimension, we can increase the drive current, and if the drive current will increase, then it will be useful in switching, faster switching. It will provide you faster switching. So for different logic applications, and mostly the processors are, if we talk about FPGAs, they are based on multiplexers. So to improve the multiplexers speed, we can use FinFET technologies. And another thing is more gate control over the channel. So even if the voltage means when the voltage is less than threshold voltage, then the device should not conduct. But that is that one will not be the case in 45 nm technology, conventional CMOS. But when we talk about FinFET, so here the gate is all around the channel, so it will have more control over the channel. So if the gate voltage is less than threshold voltage, then it will have more control in comparison to conventional MOSFET. Here still we will find some leakage current, but in this case there will be no channel, because when threshold voltage is less than gate voltage, then there will be very small current in this case. Why? Because the control of gate is more over the channel. Okay, so that is one of the reasons. So control sub-threshold performance. Sub-threshold performance means your gate voltage is less than threshold voltage. And also high speed because of increased effective channel width. I already told you that effective channel width directly improves the drain current. Then FinFET architecture. So there are different kind of FinFET architectures. Here there is single channel only. You can have vertical channel instead of planar. We can have vertical channel and gate all around it. And inside, it can be in double gate format or triple gate format. With single channel only, we can make it double gate as well as triple gate. So double gate means here the thickness at the top, oxide thickness at the top, oxide thickness at the top of the gate means top gate, below the top gate. If the oxide thickness below the top gate is higher, then it will be double gate. If the oxide thickness is uniform all around, then it will be triple gate. So double gate and triple gate FinFET. And multi-channel. Multi-channel means instead of single channel, we can have multi-channels, multiple fins. There are multiple fins, like in this diagram, there are three fins. So this way, further we can improve the current. And this is something which is fusion of, you can say, hybrid of planar MOSFET and FinFET. You can see this is first part, this is like a planar MOSFET. And one more stack, it's a kind of stacking, but it is vertically done, so it is similar to FinFET. So this is another kind of FinFET which is known as multi-channel stack FinFET, or sometimes it is also known as gate all around stacked MOSFET. So these are different architectures. Not only this, there are some literature where they have done on T-shaped fin. T-shaped fin, inverted T-shaped fin like this, vertical but fin like this. Okay, so or sometimes pie-shaped fin means somewhat this, if it will go deeper into the bulb, so that will become pie. Both sides, if it is deeper into the bulb region, then it is pie shape. So there are different kinds of FinFET architectures. Then simulation, what are the tools that can where we can implement these kind of architectures? So TCAD, there are different kinds of TCAD tools. TCAD, technology driven computer aided design. So here, why technology driven? Because it is here you can design your own technology, not only like in some of the tools like Cadence, their model files for a particular technology will be a fixed. This will be fixed like 45 nm, 80 nm, 180 nm or 90 nm. But here the designer can design their own technology, but there will be certain limitations for a particular tool, like here in this tool, Visual TCAD, there will be 10 nm, means you can go up to 10 nm technology mode. But advanced version of these tools, they are able to perform up to 7 nm, and some of them are able to perform up to 5 nm technology mode. So why these kind of softwares are important before fabrication process? Because fabrication is very costly. If we talk about normal thin film synthesis and characterization, that will be comparatively, less cost than if we compare it with the MOSFET fabrication. So MOSFET or FinFET fabrication, that are very costly processes, and that's why it requires a lot of huge investment. And to avoid those, if any kind of failure after the fabrication will happen, then then there will be loss for that company or manufacturer. So that's why they invest huge amount on the designing part also. to avoid the bigger loss in fabrication part. So that's why these kind of tools, technology driven tool are important, where the designer can develop a new technology node at lower technology, like TSMC have gone up to 1.4 nm technology node. Okay, 3 nm technology node. So up to this, if you are reducing the size of transistor, this is something related to the feature size of transistor. So you can, then the designer can pack more transistor on the same silicon area, same silicon IC area. So that is the advantage of scaling down the dimensions. But if you are scaling down the dimensions, then the performance should not performance should not be degraded. It should be under limit. So that's why here FinFET has been used. The advantage of FinFET you can see here in the diagram, that it is, the graph is near to the ideal nature, like in CMOS, and with the lower technology node also. But there are certain more designs where this graph is much sharper than this also. This is the basic simulation one. So some of the graphs are like this. It has very sharp characteristic from off to on conditions, even with the similar dimensions if we compare it with the conventional CMOS, like here. Because of this effective channel width. Okay. Now, what do you understand by sub-threshold performance? That is important thing here. Sub-threshold performance means when the gate voltage is less than threshold voltage, then there will be, there should be no current. Ideally, there should be no current, but there are certain current in practical cases. So what is the role of designer? They must assure that the sub-threshold performance, sub-threshold slope must be limited, and it should be near about 60 millivolt per decade. And drain-induced barrier lowering should also be very less. And millivolt per volt, it should be near about millivolt per volt, which is very less in terms of the value. Okay, so if this much of values are maintained, then it means that device is good. And how will you see that it is good? So you can draw the characteristic between gate voltage and drain current. Like here it is shown in this diagram. You can draw the characteristic between gate voltage and drain current. And if this characteristic is sharper enough, it means these values are under limit. If that sharpness is reducing, it means these are not suitable for switching purpose. So this is the role of sub-threshold performance, why it is important. The next thing is power consumption. So basically we are concerned for the static power consumption and dynamic power consumption. So dynamic power consumptions are short circuit power consumption. It is mostly related to the on and off process of the transistors. So it is related to frequency. But if we talk about the static power consumption, it is not related to frequency or the input. It is mainly the device property. So if anyhow we are trying to manage this static power loss or leakage current, then we can reduce the overall power consumption. It means when the device is not in use, then these powers will be almost zero, and there should be only static power consumption. So if device is idle, if anyhow we'll try to reduce this static power consumption, then we can overall reduce the power consumption. So that is the advantage of FinFET. If the gate will have more control on the channel region, then the leakage power will be less. But we are here concerned for the analog performance. Here we are concerned for the analog performance. So here you can see analog RF performance. The major parameters are transconductance. Analog we need to design amplifiers. Okay, some comparators, converters. So if the signal level is good enough, then it is fine. But if signal level is very low, then you need amplifiers also for any kind of analog application. So transconductance must be very high. Means with transconductance means the variation of current with respect to the variation of gate voltage. So it must be high. Cutoff frequency, unity gain cutoff frequency. Bandwidth should be large because if large bandwidth, it means it is suitable for the various ranges of the input frequencies and gain bandwidth products. So these are certain, not only this, some noise margin are also part of analog performance. Power consumption includes both analog as well as this logic performance. So here let us start with the application part of it. So first one is the one of the example I have taken for amplifiers, FinFET-based amplifiers. So you can like for the beginners, they can start with the understanding with CMOS, conventional CMOS based amplifiers, and then they can switch with the FinFET based you know amplifiers. So you can move forward by through two kinds of softwares. Either you can design your own transistor, like I have shown here. You can design your own transistor, and you can, after designing it, you can create a symbol like this. You can create a symbol like this and replace those conventional CMOS architecture with the FinFETs. Yeah, definitely the match, the performance in analog you may not get directly. So then you need to design an optimization process. Further, you need to increase the number of pins or the number of gate or the material. You need to change the material to optimize the performance. But for every optimization, you need to get this kind of symbol so that you can replace those CMOS based architecture with the FinFETs. So here in this circuit architecture, you can see, uh, although it seems like the symbol you may see.
Ma'am, you are not audible. Kindly unmute yourself.
Now I'm audible.
Yes, ma'am, you're audible.
Okay, okay. Fine. So my screen is visible to you.
Yes, ma'am.
So here, in this, I have already shown you that this is a model file of FinFET, because when we short all three gates together, so it will similar to the, like this is gate, and FinFET, and this is other side gate. Okay, other side gate. This is source, drain. Okay, and gate. If we join these two together, so it is single gate only. It becomes single gate only. Although it is multiple gate, but if we join them, then we can simply apply a voltage to make this on and off. Okay, so here the CMOS based design has been changed with the 18 nm FinFET. Okay, and here is the test circuit for the same. After designing it, the symbol has been created for operational amplifier, and it has been tested in cadence tool. For that, we have seen the responses that if the voltage, even if the voltage in microvolts, you can amplify it into millivolts. So it is capable of amplifying the voltages in microvolts to millivolts. So if the voltage level is very low, like biopotential, for biosensors, the voltage level will be, if you are trying to measure the charge in terms of voltage, biomolecule charge in terms of voltage, so that voltage will be very less. So if that kind of amplification you want, so you need to have an amplifier which is having gain more than 100. So if the gain will be more than 100, it means the dB, how much will be the value? So 20 log 100. Okay, so it will be more than 40, means 40, or if it is more than 100, so it will be more than 40 dB. Okay, so if we are able to achieve more than 40 dB, it means it is good for the amplification purpose. So here in this diagram, it is shown that although it is basic FinFET, it's a basic amplifier architecture with FinFET, but still we are able to manage with the gain. And it is the maximum value here is showing 40 dB in terms of dB. And the range of frequency, yes, here somewhat compromise in terms of range of frequency. If we compare it with the CMOS, so you may get range of frequency more than this, but here we are getting range of frequency slightly less. So if the designer role is to improve the gain along with the range of frequency that I said, bandwidth. Okay. The next example is FinFET based analog to digital converter. So how will you do it? Analog to digital converter, FinFET based analog to digital converter. So whenever you are going for analog to digital converter, so either you can do it with some dual slope method or flash ABC or successive approximation. So there you need a comparator circuit. So analog to digital converters are frequently used for the analog signal processing, but that requires comparators. So this is one of the TIQ based FinFET 18 nm FinFET comparator. And with this comparator, you can compare the input signal and develop a logic low or high level. So here this is input signal, and logic low and logic high is changing according to the signal value. Okay, so small part of it has been shown, although the signal may be levels kind of variations. So accordingly, you will see the changes in the output. So comparator that gives logic low or logic high based on the input value. If the input value is higher than the reference, then it will be logic high, and if input value is less than the reference, then it will be logic low. So here is the ABC, one of the example of ABC, which is 3-bit ABC analog to digital converter. And you can see here, there are how many comparators? There are 7 comparators used. So how we have replaced it? So the design which are available with the CMOS technology, we can replace the comparator with FinFET. Okay, all the transistor models with FinFET model, 18 nm FinFET model, and after that creating one comparator over there, we can replicate that as many as times we need, and we can make a design. And another block that we need is encoder. If it is 3-bit output, it means you need their encoder, which is 8:3 encoder. Okay, so here one encoder is there, which is also designed using FinFET. And encoder, you already know it's a kind of digital circuit, and where you can use some logic gates. By after designing some logic gates, you can design encoder also. And then, so this encoder is based on FinFET only, but here only block has been shown. So all the blocks here are based on FinFET, like comparators and encoder. After designing these blocks in cadence, you can integrate them, and you can evaluate the performance. So it's a 3-bit encoder. So there are three output binary bits for any analog signal. But for good resolution, we need to improve the number of output bit. So high resolution means more number of output bits should be required over here. But what is the drawback of this kind of architecture? That here, if you increase more number of bits, so you need more hardware. So that is the drawback of, means more number of comparators. So that's why that is the drawback of this kind of architecture. So designer mostly prefer the successive approximation registers, where there you also need digital to analog converter. So first you can design digital to analog converter using FinFET technology, and then you can go ahead for analog to digital converter. So here is the output response, but I have shown only 3-bit up to 3-bit. So this is your input signal, how it is changing. And according to this, we are getting different values in the binary. Okay, in binary. Now, another application of FinFET analog application is biosensor. We can also design biosensor with the help of FinFET. So in that case, this is normal architecture of FinFET, how to make it biosensor. So one of the very common method, there are several literatures available where you can create the cavity under the gate. So cavity can be anywhere, cavity can be here, cavity can be here. So because here the gates are all around, so you can create cavity, but you need to check the performance, that which one is most effective. Because if you are creating cavity, and what is the need of creating nanogap cavity? The need of cavity is to see the responses of present biomolecule. So this is normal architecture of MOSFET. If you want to measure some potential of biomolecules, so you can create a cavity region. So any biomolecule, you can replace this any biomolecule, if that will replace this air gap region, so that will change the dielectric properties of that region. So by changing dielectric properties of the region, the current will change. Okay, so because current is also dependent upon dielectric properties. Why? Because capacitance is dependent upon dielectric properties. So if you remember the basic expression of drain current, so it is dependent upon capacitance also. Okay, so dielectric properties are by changing dielectric properties through biomolecule, you may see the different kind of drain current characteristics. So here you can see, although all the biomolecules are considered as neutral, the P value for them is 0, but the dielectric constant of different molecules are different. Okay. So you can see, because of the different dielectric constant of air, strepta, vidin, aptes, and keratin, there is different characteristic of drain. So, but all are following ideal nature. So that's why we can calibrate this. We can calibrate these changes, and we can predict about any other molecule which is different from this. After making a pattern with this, we can calibrate for any unknown foreign atom also. Okay, same way here in the second diagram, the sensor is also sensing the potential. Here it is also only sensing the different material which is of different K value, But here, not only the K value, here for the same material, here the charge is also different. 0 plus 5 into 10 to the power 12 and minus 5 into 10 to the power 12. So you can see here the characteristic is different for neutral, and this is for positive, and this one is for negative. So we can although there is not much, sequence in that, but with the further enhancement in your work, you can, because this is initial level work, so here still we are we need to make it some difference between positive and negative charge, so that anyone can understand that by going positive side it is increasing, or by going negative side it is decreasing or increasing, whatever. Okay, but you can see the changes. The changes is there. It means it is not wrong. Changes is there because of different charge present on the biomolecule. We are getting different values. Okay, so it means there is chances to use this feedback as biosensor also. And biosensor can be used for biomedical purpose. They can be used for changes, detecting the changes in environmental conditions. So several applications of biosensors. And now sensors are part of most of the electronic gadgets and portable devices. So that's why a lot of work has is going on in this area. Then conclusion. So majorly this discussion is to trigger the use of FinFET for analog applications and develop new circuits. Although here the examples which I have taken mostly related to the CMOS based design, and then converted into FinFET with some bias by change in the bias and the technology level. We have tried to manage with the performance also, but you can add on some additional architecture in that for future technology, for future improvement in the performance. Okay, so the advantage of it is if we compare it with the MOSFET. So if we talk about 45 mm, because the size is bigger, so obviously it will demonstrate better speed and power efficiency. But if we go below 45 mm, then FinFET will be effective only, and because of less short channel effect. And 18 mm FinFET model files are available, which can be used to implement, implement any kind of analog or digital applications. And I already told you, like TSMC, Samsung, and Indian uh, are also moving forward for the fabrication part. So we are also trying up to 28 mm technology, fabrication of 28 mm technology node uh, in some of the manufacturing unit in India, which is targeted by 2026. Okay, so still the research, a lot of scope in this area at lower technology node in India as well as abroad. And yeah, somewhat net issues. So am I audible to you?
Yes, ma'am. Yes,
Slightly
ma'am.
audible?
Yeah, you are audible.
Okay. So this is all about my lecture. So what are those applications for FinFET? I have already shown you that it can amplify the signals up to microvolts, and so it's useful in biomedical applications. And we can design ABC and DACs with the help of FinFET also, like we do in with the help of CMOS conventional CMOS. You can design biosensors, and the companies are targeting automotive, electric vehicle, consumer electronics, telecom, and mobile phones based on printed technology. So, lot of scope based on this. So there are some additional which is not related to research, but those who are BTech and MTech students, they can have interest in this. That India is now moving forward for 28 nm manufacturing of 28 nm technology node, and they are targeting for the chips for electric vehicle, telecom, defense, automotive, displays, power electronics, power management chips. So still a lot of scope in terms of jobs. More than 60,000 jobs are now coming in this area, and these are the tie-ups which are shown in this Indian Tata Electronics with the ESMC, Taiwan, and Tata Semiconductors. Okay, so they have entered into the manufacturing of ICs. And here are some references, my contact and source profile. So thank you very much. Any query?
Thank you, ma'am, for that enlightening presentation. Audience, any questions? Any questions? So since we are not having any questions, we'll be ending this.
Thank you. Thank you very much for inviting me and giving me chance to present myself. Thank you, sir.
Yeah, thank you so much, ma'am, once again.
Okay.
So thank you everyone for your kind attention. We'll gather now at 2 p.m. here in the Central Auditorium for one more talk and the valedictory session. And your attendance is mandatory. Meanwhile, we are now going to start the technical sessions in the 4 halls, and you can join any session of your interest. Okay. And the stage committee volunteers will stay here.